In this video, we will talk about shadowing and why do we need shadowing. We need shadowing because the path loss model does not capture the environment clutter. And what is environmental clutter? Let us go into more detail of this. Let's say we have a transmitter and a receiver, and if we consider a simple scenario, there is a hill, so we will have one line of sight path, one reflected path from the hill, another reflected path from the ground, and this simple scenario will generate a single value of path loss exponent alpha at a distance of d. This implies this distance is d. Now if we go more beyond, and if we consider there are some buildings and there are some trees, and now there are scattered paths and there are more reflected paths, in this case the path loss exponent may be different, but that is captured by the path loss model. But however, if we go to some other directions, let's say if we go to this direction at the same distance d, the environment may be different. Let's say we have here water bodies, or there are some trees, there are many trees, or let's assume that this is a forest area. So the operative environment in this direction, in the earlier direction, is different from the operating environment in this direction. And similarly, if we consider some other direction, let's say in this direction or in this direction, the operative environment may be different. So what we would like to do is, we like to use a single value of path loss exponent over the whole area. So the path loss, single value of path loss exponent means we want to have a single value of alpha at a distance d, at a distance d, which may be in any direction from the transmitter. And how do we calculate is, we go to a single direction. Let's say we go to a single direction. Around this distance d, we take lot of measurements. We then average the measurements, and then we go to the next location in some other direction. We take a lot of measurements around this distance. We then average, and similarly at all the directions we take average of the received signal strength. And by taking all the averages, we get the path loss exponent. But however, please note that the operative environment at this direction is different from the operative environment at this direction, which is not captured by the path loss model, or we can say which is not captured by the path loss exponent. So we generally say the path loss is the area mean. Path loss is the area mean that allows us to use a single value of path loss exponent over the whole area, irrespective of the variations or the irrespective of the variations or the different operative environments at different directions. But whereas if we want to compute the local variations in this direction, or local variations in some other directions, or in some other directions, we need the model of shadowing. So across a distance d, we get an average path loss, and across this, if we compute the local variations in a particular directions, that is captured by the shadowing model. So again, from the figure also it can be seen that, so this is the transmitter receiver separation, and we have path loss in dB. So for a particular value of path loss exponent, there are variation. For example, for a particular value of this exponent n is equal to 5, we have signal strength fluctuations over the area mean. That is, there are local fluctuations over the area mean, and that is captured by the shadowing model. This is important because we need because in a particular direction, when we require that the received power strength at a distance d should be greater than sigma, or should be greater than some threshold value. So these things are captured by the local variation, by considering the local variations in a particular direction. So if we summarize, path loss is used to calculate area averaged received power as a function of transmitter and receiver distance, and it computes the area mean, that is transmitter, and if this is the area and this is distance d. So for the whole area, a single path loss exponent alpha can be used. Whereas the shadowing, it captures the local mean. For example, in this direction, if we had to capture the local variations, they are captured by the shadowing model. Or in this direction, we need to capture the local variation. This is captured by the shadowing model. So then, after by including the path loss, average path loss, and the shadowing, the path loss can be written as the average path loss, that is at a reference distance of d naught, which we studied earlier, that is the close-in distance. Then alpha is the path loss exponent, d is the distance of interest, and psi sigma is the zero mean Gaussian random variable in dB, which accounts for shadowing. Okay, and sigma is the standard deviation also in dB. Then the received strength at a distance d is calculated by taking the difference of the transmit power minus path loss at a distance d, and this path loss now takes into account both the path loss and shadowing, that is both the area mean and the local mean. So let us go to another figure. This is the distance axis, and this is the received signal strength. So as we are increasing the distance, there is a decrease in the strength, and this is the example scenario when alpha is equal to 3.5 and sigma is equal to 8 dB. So as a result of shadowing, it can be seen that the received signal strength fluctuates in upward direction and in the downward direction from the average received signal strength. So as a result, there is a high dynamic range of receiver is required. To account for these fluctuations, the dynamic range of the receiver has now been increased. And when we talk about sigma, the sigma can take a value of typically between 5 to 12 dB for macro cells and 4 to 13 dB for micro cells. And this sigma is independent of the distance between the transmitter and receiver. So this is what is shadowing and path loss and why shadowing is required.